Hi, everyone. My talk is on lexical complexity in software engineering. I've got to specify because I think it's part of linguistics is also called lexical complexity, but that's not what we're doing here. I work for a company called Accurx. I'm a staff engineer, but this is not related to their work. This is my own work. And yeah, let's go. So I want to preface the whole talk by saying that this is very much a talk about a journey rather than a talk about a destination. This is ongoing research. In fact, as of Sunday, I made a realization that turned everything on its head, and I've had to rethink a lot of things. So there's some very fresh thinking that I've managed to get into this talk based on prototypes I was building yesterday and today. But the underlying concepts, I believe, are strong. So the underlying concepts still worth talking about, even if the details are in flux. So yeah, let's go. In human languages, we have this phenomenon where human language can get extremely complex and extremely flowery, and it serves a purpose. It serves lots of purposes, social purposes and artistic purposes. But I don't know what this means. I don't know anyone that knows what this means. It's an impossible sentence. Whereas something like what Dr. Seuss writes is probably understandable to a 5-year-old and was probably intended to be understandable by a 5-year-old. And this is probably where we want to aim with all of our software as well. We want things to be as simple and as understandable as possible, because someone is going to have to come and work on it after we are gone. Code is not human language. It's not an art. Most of the code that we're writing is for a business, and there's a bottom line. There's no real benefit to complexity beyond what we actually need to have. Every solution will have intrinsic complexity that it has to deal with, but then figuring out how much of your complexity that you're dealing with is sort of extraneous to that is the question I'm very interested in. So here are 2 random little samples of code, and I think we can probably look at both of these. Anyone in this call can look at both of these and say one of them is simpler than the other. Now, there may be a reason to go with the second one around immutability or other reasons like that. But generally speaking, in terms of looking at it and reading it, the first is going to be simpler. But we don't really have a measure that will tell us that. We don't really have a metric. So how can we measure our code quality? I was watching a talk on connascence, which is sort of an upgraded version of coupling and cohesion, where it goes into a lot of detail about the different types and blah, blah, blah. And towards the end of this talk, there was this offhand mention of entropy. And this caught my attention because it always does. I have a background in physics. I didn't do computer science, so my brain immediately goes to statistical mechanics. But whenever I hear people talk about entropy in software, it tends to be, maybe it's the circles I run in, but it tends not to be Shannon entropy or anything like that. It tends to be, oh, the code base is getting more entropy. We need to refactor it to reduce the entropy. And I just sit there and think to myself, you don't know what that word means, and you keep using it. So yeah, we kind of talk about it as code base quality, and you refactor it away, but we're always quite vague on it. But I went back to my background. So the inspiration really struck when I started thinking about how I could apply what I knew entropy to be in software, and how I could use that to start computing code quality. And to me, it was a very interesting question. I was aware of a few metrics already, and there were others that existed that I wasn't aware of, and some of them aren't computable. But I'm going to talk about a few of them now. Yeah, I knew about cyclomatic complexity already. The other 2 I've learned of since, and one of them is mostly here as an honorable mention. But let's start with Kolmogorov complexity. It's the OG. It's from 1963. It's the length of the shortest program that can produce a given output. And actually, I was talking to Bruno just before about how you use closure macros to build programs that act on other parts of the program, and it immediately made me think of Kolmogorov complexity and how small of a program you can get to do a certain behavior to produce a certain output by doing metaprogramming and stuff like that. So I thought that was quite interesting. So anyway, an example here. If you want to produce the output A, B, A, B, A, B, A, B, A, B, you can do the complex version or you can do the simple version. And complex and simple here means shortest program. That's it. It doesn't mean anything more detailed than that. But the problems I saw with this immediately is that homograph complexity is a property of the output of the program, not so much of the code that you are writing and maintaining. It's not computable, and it's really not connected to human comprehension. It's much more about optimal computation and things like that, right? So this is sort of the oldest concept of complexity I could find in computer science, and it doesn't really do this whatsoever. It doesn't really do what we want it to do whatsoever. The next is cyclomatic complexity. My mouth is already dry. This is the one that I knew about. I'm sure a lot of you know about it. It's from 1976, a guy called Thomas McCabe, is it, I think? And it's the number of independent paths through your code. You could also think of it as the number of decision points in the code. There's also like a graph theory interpretation of it, which I think is where it originated from, that I can't exactly remember right now. But it's very, very mathematical, and it's very well established, but it's also got its critiques, which I think I'll get to a little bit later. But you can roughly think of it as the complexity of execution of a sample of code. So, oops, I haven't moved on the slides. There we go, we've caught up. Cyclomatic complexity. There we go. Sorry, I got confused. So, hang on. No, I'm going to leave it. So here's a sample of code. It gets the sum of primes. It does it in a very, very basic way. It's not using the sieve of Eratosthenes or anything like that. It's just take a number, check everything below that number up to that number, and make sure that none of them divide. If any of them do divide into it perfectly, then you continue, you skip out. It's not a prime, it's got some factors, etc. So it does it it's a very brute force approach, but the point of it is just to demonstrate the complexity. So if we look at the decision points, cyclomatic complexity, a function itself is a decision point. So that's a +1. And then there are the conditionals within the for loops. That's another +1, another +1, and then another +1 on the actual if conditional itself. Shouldn't be any surprises here. This function has a cyclomatic complexity of 4. It's useful, but it's limited to branching conditionals. Any other complexity from this function is completely invisible to cyclomatic complexity. For example, the depth of the nesting, any complexity in the statements themselves, anything like that, you can't say. It's also been criticized because of its high correlation with the lines of code, I believe. And I think the main criticism that you tend to see is that it's not very good at predicting bugs, because you can mostly just use the lines of code to predict bugs. But we'll get onto that as well. Yeah, cyclomatic complexity. And then the next one that I learned about last time I gave this talk, actually, was cognitive complexity. So this is relatively recent. It's from G. Ann Campbell in 2023. And this is measuring the cognitive difficulty of reading the code. So there's a set of features and rules that are defined in the white paper that define when you add and how you add points. So back to that same sample of code. I'm not going to go through all of the rules because frankly I don't remember this. But effectively, you're looking at the basic assumption of cognitive complexity is that there's a basic rule of reading software that is that you read from top to bottom, and anytime you have a piece of code that violates that, for example, a for loop, where you have to get to the bottom of the for and then jump back up to the top, or a continue where you jump out of the loop, any break in the continuity of reading from top to bottom is counted as a point of complexity, and you also increase the strength of those points by whenever you nest inwards. If I'm being honest, I'm not 100% sure why the continue isn't a 4-pointer, but this is taken directly from the white paper. So anyway, this has a total of 7. So this is capturing arguably very, very similar things to cyclomatic complexity, but it's also capturing the depth. So I would argue it's better representing the complexity of this system, of this piece of code, than cyclomatic complexity did. I'm not aware of any studies that prove this being useful to predict bugs. The gold standard of any sort of scientific endeavor is to have predictive power. I don't know that it has that. I haven't looked into it. But intuitively, it does feel like it's doing something to me. But neither Kolmogorov, cyclomatic, or cognitive complexity can give any sort of view on which of these is more complicated, even though we can look at it. Oops, the other one is an old version. Even though we can look at it and say that one of them is more complicated than the other. So what do we do? Hypothesis. Complex things are harder to understand. Modifying code. So I came up with these sets of hypotheses. Modifying code correctly requires understanding it. Complex code takes longer to work with. Complex code is more bug prone when modified, and therefore complex code is more expensive. What we still need to make any of this meaningful, though, is to find a way to analyze the complexity. Now, what I've started to believe and learn the longer I've done this project is that we do have ways of analyzing the complexity, but we have ways of analyzing complexity and that only capture certain types of complexity, and there are other types of complexity that are left out. So I think that what my hopes are for my lexical complexity metric is that it informs a suite of tools that we can use to analyze the totality of the complexity, because complexity has a lot of different there's a lot of different arms to it, right? There's a lot of different ways in which something can be complex. Anywho, what I want my system to do is it should be static analysis, and it should be language agnostic, and it should reflect the human experience in some way. So back to entropy. Entropy is often misunderstood, as I was saying before. So we're going to do a quick primer. So classical entropy was from 1865, back when they were talking about heat engines as their primary thing in physics. And this guy, Rudolf Clausius, noticed that as you were heating and cooling in a heat engine or something like that, there was like a reduction in the amount of energy in the system that was able to do work. And this is always interesting to me. I always like to think of code when I think of this, because you can imagine a code base that hasn't been refactored ever, and there's not much energy, there's not much leeway in it that will allow you to move forward and build new features, because it's sort of locked into the old behaviors and everything becomes very expensive. Whereas doing a refactor puts energy into the system, so it's got more available to do work. I always think of this when people talk like that. So this is the original sort of thermodynamics entropy, and it's made famous by the arrow of time. You can't uncrack an egg, and the heat death of the universe, which will happen in 10 to the 100 years or so. Cool. It was followed by Boltzmann entropy and Shannon entropy. I'm assuming you will all be fairly familiar with Shannon entropy, and Boltzmann might be new. But we're going to start talking about Shannon entropy, because when I started the project, I didn't base it on this because I wasn't very educated on it. So in information theory, Shannon entropy is a measure of the surprisal of a system. It's the amount of information, roughly speaking, it's the amount of information that each element of the system carries, weighted by its probability, right? So if we're just talking about surprisal or self-information, it's a very simple formula. It's log of p, where p is the probability of that thing happening. So for high, minus log of 5/6 versus the surprisal of bi is the negative log of 1.1/6. The bi is significantly more surprising, so the surprisal is way, way higher. It's 2.58. And that's because it's less probable, right? Shannon entropy is here. You'll recognize the log p term at the end. And all we do is we attenuate that by the probability of it actually occurring. And then we sum them all up, and then we have our entropy. That's all entropy is. It's an accumulation of the self-informations. There you go, just like I said. So if we run through a quick calculation, the other difference is that a single message doesn't have entropy as such. A single message only has information. The system as a whole has entropy. So if we take those numbers from before, the minus 0.26, minus 2.58, the 5 over 6, the 1 over 6, and we add all of these together, we find the entropy of this high-pi system is 0.65. Okay, I'm going through this because I want people to have a feeling for the equations without them feeling intimidating. So hopefully that's working. And it's not just very dry maths, but let's move on. Hopefully all of that makes sense, but we're moving on. So Boltzmann entropy. This is the one I actually knew about. This was my entry point to the project. It cares about the physical properties of systems with many elements. It's from statistical mechanics. Statistical mechanics is basically like quantum thermodynamics. It's thermodynamics when you're thinking about individual particles rather than, heat and temperature. So Boltzmann entropy is all about, well, it's the exact same equation. The only difference between this equation and the Shannon entropy is that we don't do log base 2. We use log to the base of e, otherwise known as the natural log. And actually, you can do the Shannon entropy with natural logs. You just call them, the units are just different. I think you can vote by multiplying it by 2.3 or something. And that KB term is the Boltzmann constant, which is not super relevant. It's a very large number. That's all we really need to know. Or a very small number. I don't remember, but it's just a number. But yeah, it's exactly the same. But it simplifies to S equals K ln omega if all the microstates are equiprobable. And this is the equation that I had in my head when I first started doing all of this work. So it's the equation that I used. So omega here is the number of microstates that a system can occupy. And I'll explain what that means very shortly. But yeah, that's what we do. So if entropy is defined as S equals K ln omega, K the Boltzmann constant, which we'll ignore, the natural logarithm, and omega, the number of microstates in the system. Or available to a system, the number of microstates it can occupy. So to explain microstates, let's imagine you have two apples, one is red and one is green. Imagine no longer, there they are. You can rearrange these in two different ways. You can have green-red, you can have red-green. It's very exciting. These are two different microstates that your system of apples can occupy. We're only giving them one degree of freedom here, which is the order they're in the list. In physical reality, there's going to be the position, there's going to be the velocity that they've got, there's going to be charges and all sorts, but we're simplifying. See, two microstates, nice and easy. So if we pull back our formula, we're going to drop K because it doesn't matter very much. We have two microstates, so omega is 2. The natural logarithm of 2 is 0.69. Okay, it's a little number. Okay, now let's say we have 5 apples. There's a lot of ways to arrange these. There we go. In fact, it's 5 factorial. I wish I hadn't hidden that next slide. No, actually. Okay. But you can imagine you have yellow, red, green, blue, purple. You could also have yellow, red, green, purple, blue, and then you do that a million times. It's just combinatorics, and we all learned it in high school. But it's 5 factorial, and we end up with 120. So from just increasing by slightly more than doubling the number of elements of the system, we've increased the number of microstates by 60 times. Now, the natural logarithm of that, of 120, is 4.79. So we've massively increased the entropy of the system when we've only sort of doubled and abetted the number of elements. So let's try to apply some structure to these apples. And this was the real brainwave that I had. Let's put them in boxes. So now we have 2 boxes, each with one with 3 apples, one with 2 apples. And now we have much fewer rearrangements if we're still preserving the structure. You can rearrange the boxes themselves. You can rearrange please. There we go. Okay. You can rearrange the apples in the first box, and you can rearrange the apples in the second box. In total, this gives us 24 different microstates that the system can occupy, as opposed to 120. And when you add up the natural logarithms of all of these bits, you end up with 3.178. Isn't that interesting? So without any structure, it was 4.79, and with just a very basic structure, it drops down to 3.18. So just by applying structure, we've reduced the entropy, which is, I think, very interesting, because I think a lot of what we do in code is about structure. It's about organizing code, and it's about structuring information, and it's about applying structure to what would otherwise be completely procedural. But anyhow, let's apply this to code now. Imagine you have two files with the same content, roughly. One is one large function with 1,000 lines, and the other is 4 smaller functions with 250 lines each. If we apply the exact same logic, treat the lines of code like an apple and treat the function like a box, file 1 has an entropy of 5,900, whereas file 2 will have an entropy of 4,500. So just by splitting them apart, again, you've reduced the entropy. Just by reducing the massive bulk of information that would exist in one giant function, you reduce the entropy. And as experienced engineers, what would be your first feedback for a 1,000-line function? Can you try splitting this into smaller functions, please? So this S number seems to reduce as we refactor our code. Okay, I'll be honest, this is when I was getting a bit overexcited. And my thinking has moved, honestly, back to it being entropy. But anyway, at the time, it seems to measure complexity. I think that what I really believe now is that we can apply entropy in the computation of complexity, which makes sense, because entropy is all about information and complexity is all about consuming information. So let's move on a little bit. Lines of code seems a little bit crude. Lines of code seems a little bit crude. I think there's more we can do. I'm always interested in, the micro complexity of individual lines of code as well. So let's talk about abstract syntax trees. So I'm assuming most of those are familiar. If you're not, the abstract syntax tree is what your compiler or parser is passing your code into, so that the execution, gosh, I'm so bad at I'm forgetting the words. Anyhow, this is how your code gets represented to the compiler or whatever we use in Clojure, the interpreter, in order to actually get ready to be executed. This is the actual data structure of the code. I genuinely have no idea how that applies to Clojure now that I think about it, but in languages that I do know. So this is TypeScript, for example. And you can see that there is this yellow line, there is a source file. And in the orange line, there's a syntax list that contains everything. And there's an expression statement which contains everything again. And that first bit is the call expression, which is the console.log, which has a property access expression, which is again the console.log. We have a console, we have a dot, and we have a log. Very exciting. And then there's the open param, the syntax list, which is the stuff that goes between the params. And within the syntax list, all we have is a string literal. Then we close the paren, and then we end the file. Yeah, so this is the abstract syntax tree. And I looked at this and I said, why can't we apply the same kind of structure analysis to a tree? Let's go for it. Let's do it. So if we do the same analysis here, we're ignoring anything that only has one child, anything that only has one sort of rearrangement, because the natural logarithm of 1 is 0, so is log base 2. Sorry. So we're ignoring the syntax list as well. There we go. And then this one has 4 children, so we can say 4. It's the open paren, it's the closed paren, it's the syntax list, and the property access expression. And then this here, again, that's a 1, that's another 1. And this one has 2, the syntax list and the end of file token. So that's a 2 factorial. So in this case, by analyzing the abstract syntax tree, we can apply an entropy to that line of code, which is 5.66296, which is very cool, right? So we can apply the exact same logic that we had before, the exact same stuff that allowed us to punish lack of structure before, here. So let's increase the complexity of that code sample. Now we're just setting a variable, which is the greeting, and we'll console log the greeting. And we can see there's a significantly larger abstract syntax tree. I'm not going to explain every single bit of it because we don't need it. We don't need to. But here are the non-zero elements of complexity in there. And if we add all of those together, we get 8.84. So by increasing the actual complexity, we can now measure a complexity or an entropy, a complexity that is sensitive to all the things that cyclomatic complexity doesn't see and that cognitive complexity doesn't see. And lines of code wouldn't see if you just put a semicolon and put them on the same line, but the system would spot that as well. So, okay, this next slide is a bit early in the deck, but basically I went and built this. I went and built this, and I also built a VS Code plugin to display the highlighting to show you the bits that it was targeting as the most complex. There's more. This is not the right place to have this slide. Sorry, I keep playing around with the talk, and I've definitely not figured it all out yet. So let me get my head around what I want to say here. So in the computation, what we do is we take the code and we pass the abstract syntax tree. We actually use something called tree setter. I'll get into it a bit later. And then we apply some depth factors as well to punish you for going deeper into the system. And yeah, we just apply that same analysis to every single node in the tree, in the abstract syntax tree. And the idea is that we'll be able to spot nodes that have lots of children and nodes that branch out a lot and nodes that are very deep in the tree. And we will highlight those and punish those. So you'll see the green segments are areas where my system thinks the complexity is low. And then the red areas are the places where it thinks the complexity is high. Some of these make more sense than others, I will say. It doesn't particularly like the word smooth on line 17, which I think, anyway, we'll get to it, it's fine. And then the document query selector header. I think these pieces are largely being punished because there's lots of sort of property access things going on here, and there's lots of the arguments embedded within that, and there's more dots, and then there's and they're also nested deeply within a structure of ifs and lambda functions and things like that. So I understand why it's highlighting these as complex, although arguably it's not doing an amazing job. But this is the much older version of the algorithm, but it is a nice screenshot. So anyhow, I just wanted to give you some example of how it would apply to reality. Okay, but you know what else is a tree? So if we can do all of that analysis on the abstract syntax tree, there's something else that's a tree, and it's the file system. So we can apply the exact same analysis to the project structure itself. And this is the bit where I start getting very excited, to be honest. So this is the file structure of my actual analyzer, or at least it used to be. And look at all that. We have the paths, we have the parsing, we have the maths, and we have the source, and all of these have different numbers of children. And what's really interesting is then you can combine the tree, the file system tree, with the actual syntax trees, and you get this sort of mega tree, which is the full tree of the file structure of the project, along with all of the individual abstract syntax trees of the code files within it. So you end up with a universal measurement of software quality, software complexity that can hit any project, any structure, any line of code, and arguably any language. And it can go to any level of granularity, like a single letter or the entire project, arguably even like the organization in GitHub, and figure it all out like that. And this is what I've been calling lexical complexity. And I call it that because it's the complexity of the actual language that you're writing in, rather than anything else. And I think it's really important to differentiate, because there's certain complexities, and I've not put it in this talk, and I should have, but the best example is there are some things that are very, very simple to write, but very, very complex to understand. Like, oh bugger, I forgot the name of it as well. The French guy. Anyway, fractal equations is the example that I'm thinking of, and if it comes to me, I'll say the name later. But an actual equation for a fractal tends to be very, very simple. But if you were to try and modify it in some interesting way, you would need to have like a master's or a PhD in maths, right? So lexical complexity is only one dimension of the complexity of software, and I think it's important that we don't try and ask it to answer every question. And the same is true of psychometric complexity and cognitive complexity as well, for what it's worth. Cool. So this measure may seem arbitrary, but it's a computational property of software systems, and it can be tested empirically. It's deeply inherent, and having said that, there is a criticism that the abstract syntax tree is somewhat arbitrary, because a lot of the structure in it is there to make the compiler happy, rather than anything else. But we'll get onto that later. Put a pin in that. So speaking of testing empirically, so I had the idea. I got very excited. I prototyped an analyzer in TypeScript. You've already seen the feature because you've seen the VS Code plugin, which is way in the future from this. But I did prototype the analyzer in TypeScript at first, because it was what I was working at the time, and you can just parse TypeScript using TypeScript native libraries, and it was very simple. So I did that. I analyzed 100 repositories, and I saw this. So this isn't surprising. As the number of lines of code increases, the complexity increases. Software programs that have more stuff are more complicated. It's a lot of graphs from here on out, by the way, so I hope you're ready. I think this is very natural. It's like saying things that are larger are heavier. Generally, yes, this is true. So this didn't tell us anything too much. But the thing that I did see that started to get me excited was this. So complexity per line of code versus lines of code. So as projects get very large, there was a very slight negative correlation with the complexity per line of code. And this could mean a couple of different things. But what I took it to mean was that there's a bit of a survivorship bias. Projects that survive to become very large and still successful, because this was a list of like well-known projects, well-known TypeScript projects. For a project to survive and be successful, it needs to manage its complexity better. And the ones that manage it worse tended not to survive. That was my reading of this. But most importantly, what it told me is that I was actually measuring something here that was real. It wasn't just random noise, which encouraged me enough to move forward and push forward, which I did. Problems with the prototype, it was language specific. It could only do TypeScript and JavaScript, and it was hella slow because it was in TypeScript. One of the targets of the analysis was Microsoft TypeScript, the actual repository, and it took about 8 hours to analyze. This was not good, obviously. So what I did was I discovered something called TreeSetter, which is a GAST parser, generic abstract syntax tree parser. It supports hundreds and hundreds of languages. My system currently supports 17 of those languages, but adding new languages is very trivial, although it won't be in the future, but I'll explain that later. So I pulled in TreeSetter, and I rewrote the whole thing in Rust. I picked Rust because I knew a little bit of Rust and I needed something extremely performant, and I fancied that more than C#, or C++, sorry. So I got a massive speed increase. I could now analyze Microsoft TypeScript in about 40 seconds, I think it was. But this was only the beginning. I continued to optimize and I continued to expand. Now I can do a full analysis in mere seconds. I can do a full history analysis. So I can point it at like Microsoft TypeScript or any repository, and I can analyze everything from commit 0 all the way up to today. And you can see the sort of life cycle of the project, which is very fun. And you could argue would be somewhat useful if you wanted to, because what you can do, I'll show you in a second, I'll show you right now. What you can do is you can start digging in. So this is my array of graphs that I published from my sort of early research. And this is NumPy, I believe, which is a Python library that does math stuff. It's very, very popular and it's been around for a long time. And you can see there's lots of these sort of jagged changes, especially in that one at the bottom middle, which is complexity per lines of code over years. But let's take a closer look. So here we see the complexity, which increases as time goes on. I don't think this surprises anyone. Software projects are a whole lot better at adding stuff than removing stuff. This is a universal law, I think. Although you can see places where it spikes up and it spikes down, and often this is because, well, what it is interesting to do is to do a bit of archaeology. Like you can look at these points and you can jump in and you can start investigating, like, why did it drop down by like 0.5 percentage points here? Like by a whole 10% here. Why did it jump up over there? And usually it's to do with the developer realizing that they had a bunch of library stuff pulled in by accident and they need to delete it, or the developer stops including generated code in the Git repo and things like that. The really big ones tend to be really like dramatic changes. But what I was starting to realize was that there was no like stable amount of complexity that would be the right amount of complexity for a project. Not that you could tell programmatically, at least. But there is arguably something interesting here, which is the complexity per lines of code, the normalized complexity. So how are you actually managing the complexity that you do have in the code that you're writing? And this, we can see some real interesting chaos. It fluctuates up and down. It makes very large jumps. It makes very large drops. And if you went and found those specific commits, you'll always find like a very large PR that does something very dramatic. I can't remember what any of these are. This was probably 6 months, probably a year ago that I was doing this now. But you'll also notice that it's sort of very stable between 13.4 and 13.9 complexity per line of code. And this does seem to be like reasonably constant across all the projects I looked at. Like you're usually looking at somewhere between sort of 10 and 15 complexity per line of code, which does make sense. I think there's a certain amount of complexity that we can sort of handle in a single phrase, in a single package, as human beings. I can't believe it took me this long to say it. None of this is thinking about AI. First off, the project predates LLM programming. Second off, I have absolutely no idea if humans will even be reading code in 5 years. I'm just going to pretend that we will because I enjoy it and my project doesn't make sense if we're not. Although arguably LLM-driven code is even more in need of guardrails than human code is, especially as we sort of drive out bravely into the slopocalypse and AI eating its own tail. But we'll see. It's an exciting world to be in. Okay, I think that was everything I had to say about this. And yeah, complexity per file. This felt like a little bit of proof positive of something happening. We've got like a sort of steady negative correlation as the team managing this decides to split things out into smaller files and manage complexity a little bit better between all of their files as time goes on. Like where before we're hovering very cleanly between 13.4 and 13.9. This is a very small variance over a very long time. The variance of the complexity per file goes from 10,000 down to 7,500. That's a very big drop. That's like an attitude change. And you can see like big portions of that drop are in sort of specific like 1 year period or something where they were like actively breaking it down and refactoring. So it's really interesting to do a bit of archaeology with this full history analysis, I think. Very dry mouth. The next thing that I did was this. Hello. So this is a plot of complexity against lines of code for, I can't remember the size of the data set. That is not good of me. But these are individual files. Each dot is an individual file. And we're talking about thousands of files, maybe tens of thousands. But I did this across many languages because I supported a lot of languages at this point. I think probably 15, 16 languages. And I found that the different languages had very different characteristic curves. I don't really want to call them curves. I more want to call them shapes. So for me, if you look at C# and Java, they look very similar. There's certain distinct differences between them, but they feel like they're in the same family to me, especially when you bring in something much, much different like JavaScript, much more chaotic, much less regimented. And then TypeScript is an interesting, fun one because it feels like you've kind of glued the C# one on top of JavaScript, which makes sense considering who wrote TypeScript. And then we have HTML, which apparently has an abstract syntax tree. If I'm being honest, I added it just to see what would happen. But again, it's a very, very different characteristic to the rest of them. First off, the lines of code never seems to get so big, and the complexity never seems to get so big either. So it's much more sort of bounded. And then I added Rust because that's what I was working in, which seems to have sort of the cleanest relationship between lines of code and complexity out of all of them. And I have a theory that this is because it's a very regimented language. But honestly, I didn't figure it out. But what this told me, again, is that I was measuring something real. Because my big struggle through this whole project has been trying to figure out if this is just like wild speculation based on a cool idea that I had, or if there's something really like fundamental that underlies it all. And these were my early attempts at figuring that out. This is all of the different languages overlaid on top of each other, crudely overlaid on top of each other, just to demonstrate, just to draw a bit of a picture. But you can see that they all of them follow this sort of very strong relationship between lines of code and complexity. And then there's just detail in how they scatter, especially towards the bottom. Cool. This was another thing that I did. So my slides aren't very good, I'm sorry. But I did a bunch of analysis. So what I found was that most of the time, lexical complexity and cyclomatic complexity correlated quite strongly, and both of them correlate to the number of lines of code, right? Which was kind of dispiriting, because what I really want is for lexical complexity to be measuring something unique compared to cyclomatic complexity. But it didn't necessarily seem that it was too much or a lot of the time. But what I decided to do was normalize both of them. So when you take out the lines of code from both of them, you take out the that very strong correlation that they share, then things get a lot more interesting. So what I did was I analyzed, I think, 6 or 7 different languages. I did 100 projects in each language, and I looked at how cyclomatic complexity and lexical complexity correlated. And I started looking into where that correlation might come from, which I'll talk about in a minute, unless I embarrassingly forget. But most of them look like this one, this Python one. So you have like largely a normal distribution, right? Arguably a multimodal distribution, but there's not really enough data. And they all had, on average, there were some projects with negative, but on average, the languages as a whole would have a positive correlation between lexical complexity and cyclomatic complexity. And what this, I think, means is that the files that tend to have lots of control flow complexity also have lots of lexical, linguistic complexity in the code that was being written to manage that control flow. There was one exception to this rule, which I didn't discover until I already booked this talk out, because I hadn't looked at Clojure yet. Clojure is the only exception where on average there was a negative correlation between cyclomatic complexity density and lexical complexity density. And I never managed to figure out what this means or why this is. I think as of like a week and a half ago, I started looking into it again, and I realized that actually this number is incorrect. It's not minus 0.13. It's more like minus 0.05, but that still leaves it as the only negative one. The reason this one is wrong is because I was doing a lot of LLM-driven work with Claude as my wonderful research assistant. But we pulled down this Clojure analyzer library that I can't remember the name of right now, which only originally handled CLJ files, but we also needed to handle two other types of Clojure files that were like compiled. I can't remember, I'm not gonna lie. The data files as well, it was something like that. Anyway, point is, one of them was not having the cyclomatic complexity computed correctly, because my system can analyze the lexical complexity of Clojure very easily, but I had to find a specific program to handle cyclomatic complexity in Clojure. But anyway, it's still the only negative one, and that's still very interesting. And that means that the places where you have control flow in Clojure, you tend to have simpler linguistic constructs. And I don't know how that happens or how that works, but maybe that makes sense to you guys. But yeah, very interesting. The other work that I did was I was trying to figure out what were the key factors that we could use to explain why the correlation was different, to explain the variance in the correlations between lexical and cyclomatic complexity, because each project has sort of varyingly strong or weak correlations, but they tend to be very certain because of the number of files in each project. Like they tend to be fairly weak but very strongly defined. So I was trying to look into this and trying to figure out how this variance was explained, and I found that about 20% of that variance was defined by language, which does make sense. Like the one I showed you earlier, Python. This was one of the higher ones with the mean R at 0.29. Let's see where this green line is. This green line, where there is the 0. C is about 0.35. I think TypeScript is like 0.2. C# is 0.2, and then obviously Clojure at 0.05 or something, minus 0.05. They all have these very strong things, and language explained about 20% of it. I then did a bunch of sort of trying to identify the domains of the different projects. I analyzed about 500, 600, or 1,000 projects, I think. Trying to assign each of them a domain and see how much the domain that they're trying to solve informs the correlation between cyclomatic and lexical complexity. Because you can imagine there's actually going to be, I didn't add this into the talk. There's going to be, you can imagine sort of 4 quadrants, files that have very low cyclomatic complexity but very high lexical complexity are going to be sort of very large dictionaries of configuration content where you're not doing any control flow stuff, but you have a lot of stuff there. Versus where you have very low cyclomatic and very low lexical complexity densities, where basically very simple files that don't do very much. High both tends to be lots of control flow with lots of complex regexes and lots of complex conditional logic and stuff like that. This is sort of the danger zone. And then very low lexical complexity, very high lexical complexity density. Very low lexical complexity and very high cyclomatic complexity, which is where Clojure sits. I didn't figure that side out, to be honest. But yeah, anyway, I was trying to figure out how much the domain may have influenced the variance, and the domain is maybe 0.9. So there's probably like 60% of the variance of this correlation that is not really explained by anything and is arguably just like the personal style of the people working on the project. But I didn't get any further with that research. Sorry, that was a bit scattered. Moving on. There was a problem. There was a problem with all of this that I've actually foreshadowed a few times in the talk because I'm older and wiser now. There are 2 problems. Okay, there are 2 problems, but I'm only talking about one right now. First off, the lines of code. So the lexical complexity correlates with the lines of code at about 92.5% with this version of the algorithm. This to me is a problem because what's the point in the metric if it's not really telling you anything that the lines of code isn't? But maybe it's telling you something within the lines. So if we normalize it, this was enough to keep me happy until the final nail hit, which was realizing the AST size correlation. So the lexical complexity, as I compute it, is very, very strongly correlated to the size of the abstract syntax tree, which is very annoying because there's a lot of difficult maths and analysis and tree traversal that I wrote to get an interesting number at the end, when you could get basically the exact same answer by just throwing all of that away and just counting the number of nodes. For me, this was too much of a problem to ignore when I realized it. And I think part of the problem is that ASTs are very regulated. There's a lot of structure that's just in place to inform the compiler or inform the execution engine. I'm not good at compilers. What each thing is and how to engage with each thing and how to pass each thing. So there's a lot that's in that, because if you actually look at this, and I'll get onto this more later, there's so much cruft in this abstract syntax tree that has nothing to do with what the developer actually wrote. You know, there's a var. Where's my mouse? Oh, come back. There's a var, there's an identifier, there's an equals, there's a string literal, and a lot of cruft that's nothing to do with them. So, and the average out degree, which I haven't even mentioned this yet, but the out degree is the number of nodes that are children of the node you're talking about. And talking back to the apples, this would be how many apples are in the box, right? So we use the out degree, we take the factorial of the out degree to find the number of ways of rearranging, or the number of microstates of those children. Or really, in reality, the entropy of those children. The entropy of that node. But the average out degree being around 1 means that there's a lot of not very interesting nodes is ultimately the problem. You can't normalize this one. You can't have complexity per node because it's all basically 1. That's exactly as I said. I can replace all my fancy maths with len tree. So how can we possibly break the correlation? This is a problem that I've been struggling with for a while. And part of the answer is that we probably don't want to completely break the correlation because it makes sense that the more stuff there is, the more complex it is. That's still a truism. But 99.7% is too much, you know. So my first thought was maybe we can do some small tweaks to save me. There are 2 factors in the equation, which is the unit complexity. One of the axioms of the system is that every element in the system has a unit complexity. It has a minimal complexity, right? And then another axiom of the system is that things that are embedded deeply are more complex because you need to understand the context of all of its parents in order to understand what it's doing. So what I did was I did a parameter sweep across the unit complexity, which is G, and the depth factor, which is D. And what I found was that there was nowhere where they stabilized. It just sort of pieced out in an asymptote forever. And I also found that there was a problem with the depth factor. The parameter sweep wanted to use something that was very, very, very low, because when you use a depth factor that is greater than 1, because of how deeply nested everything is in the abstract syntax tree, you end up with these numbers completely exploding, which was a big problem. So the parameter search did help me for some time, but it didn't actually solve any of the problems ultimately, even though I thought it did at the time. Yeah, as I said, we fixed the complexity exploding at depth by suppressing the depth factor, which actually arguably destroys the signal. We didn't fix the correlation though. The normalized complexity approach that I was talking about, the complexity per lines of code, It found interesting patterns, which is the correlations between psychomatic and lexical complexity, but it didn't resolve the core issue. We still have that actual problem. We could have replaced all of that with just the length of the tree or the size of the tree. So the realization I had a couple of days ago was maybe we're actually talking about the wrong tree. My two options that I'm currently exploring are using a different tree and breaking the log of the microstates assumption. So let's talk about the tree first. It's not only a signal to noise ratio issue, but there is a signal to noise ratio issue, but there's also like a structural issue, right? So how much of this abstract syntax tree, the same sample I showed you earlier, is actually what's happening in the code base? What's actually happening based on decisions that the developer has made, or things that the human developer has to read and understand? Actually, very little of it. Basically, like half of it. Is that even less than half? It's like 4 of the things. So I came up with this idea of a syneme, which is it's like a syntax phoneme. Phonemes are the phonic components of language as of spoken language that you use to compose words. Synemes are irreducible and are composed into statements. So, for example, this is Python now because I did the prototype in Python. Greeting equals hi, current greeting, very simple. But now instead of the abstract syntax tree, which I'll be able to show you in a minute, now we have this syneme tree, which is got a root. It's got greeting equals hi, which is the first line, and that decomposes into greeting equals, and then some quotes, which has hi. I'm debating whether the hi and the quote should be nested. It's not important right now. And then the second line is just print, greeting, which is print, braces, greeting. Much less deeply nested, much less saturated with unnecessary structure. Like this is the actual thing that the human is looking at and trying to understand, right? Or much closer. Compared to the abstract syntax tree for that same thing, we have modules, we have assigns, we have targets, we have values, we have expressions and calls and functions and arguments, and it's not even clear what's happening, frankly. And it doesn't really reflect the experience of reading the code, I would say. It does make me wonder how much of the results that I got from using Tree Sitter was a result of, was actually like really that closely related. Because I think in TypeScript, you can look at these trees and you can say, oh, I can see where these things are. I can see how things make sense. I wonder if in different languages it's less clear. But anyway, so this is what I've been looking at most recently. I was building this prototype literally today, and I've started to get some good results. I think I may have included them in the talk I did. But that prototype includes breaking this assumption as well. So the ln omega assumption, I did say this earlier, but I didn't realize at the time when I was first building this that this is what I was doing. This equation only makes sense if all the macrostates have the same probability. And it's exactly the same in entropy. If all of the messages have the same probability, then the entropy equation degrades to this as well, I believe. Oh, I had the same slide twice. If you don't have equiprobable states, then we use the original equation, the equation that's much more like entropy. So I've been prototyping the new trees approach. I've been prototyping the new entropy calculation. I've been continuing to learn. And so far, it's looking promising. So these are the results that I generated today based on the new syneme tree prototype in Python. And this is a parameter sweep of D, just looking at the depth exponent, because it seems to be the most important one. And you can see on the left-hand side, that is the correlation between complexity and lines of code, which starts off at 0.8 and goes down to 0.63 or something, depending on what we use for the depth exponent between 1 and 2. So that if the depth exponent is 1, it's like a linear relationship. And if the depth exponent is 2, it's more like a as in like the complexity increases linearly with the depth. And if the depth exponent is as much as 2, then it'll increase quadratically, you'd square it. I arguably should go and do some theory and figure out what that should actually be rather than doing parameter sweeps, but I haven't figured out how to do that yet, so here we are. And anyway, on the right-hand side, I also wanted to see the correlation of the complexity to the tree size, because I didn't want another situation where you can just count the number of nodes in the tree and have the same answer. But you can see both have really effectively broken. If you remember before, for the lock correlation, it was 92.5%, and for the tree size correlation, it was 99.7%. So this new approach really does seem to be measuring something more useful, and that's probably because it has much richer structure and much more variance in the nodes compared to the abstract syntax tree, where everything is very regimented. So yeah, that was probably quite an unusual talk for the Clojure group. Thank you all for listening to me ramble about maths and information theory for an hour, or however long it's actually been. If you want to follow me on LinkedIn, there's a QR code. If you want to learn more about my project, there is a link to my website. And if you want to get a job at Accurx and happen to live in London or be willing to relocate to London, please look at our careers. And yeah, that's my talk. Thank you very much.